Welcome to episode 37 of SpaceTime Cafe, Splitting the Unsplittable. Today's video tackles the challenging yet fascinating topic of fair division in computer science, especially as applied to real-world scenarios like splitting restaurant bills, dividing chores, and more. We explore optimal segmentation of weighted sequences under fairness, loss, understanding how these complex problems scales up to critical systems like databases, memory management, video streaming, and privacy logging. Discover various methods from dynamic programming to innovative spectral pairing algorithms designed to minimize imbalance and optimize performance. Whether you're a tech enthusiast or just love solving puzzles, this deep dive will leave you with valuable insights into algorithmic fairness and the hidden rhythms within data.
Welcome, deep divers. Have you ever found yourself in that classic situation, trying to split a restaurant bill fairly, especially when, everyone's ordered completely different things?
Oh, yeah. That can get complicated fast.
Right. Or maybe dividing up chores, trying really hard to make sure nobody gets stuck with all the awful tasks. It feels so everyday dividing things fairly. But what if those things weren't all equal? And what if the order they showed up in actually mattered? I remember this one time trying to split a bill, maybe 8 friends, and everyone ordered wildly different stuff. Apps, mains, desserts, total chaos. It honestly felt like some kind of NP hard problem just to get it truly fair. And that was just, a few dollars, not a whole database about to crash.
Exactly. It scales up.
So today we're taking a deep dive into a really, really fascinating area of computer science. It explores this whole idea of fair division, but on a massive critical scale. We're digging into this amazing lecture. It's titled Optimal Segmentation of Weighted Sequences Under a Fairness Loss.
Sound intense.
It is. But our mission, like always, is to pull out the key insights, understand the why and the how of fair data partitioning, and maybe uncover some surprising facts that might just mess with your intuition a bit.
Okay, I'm ready.
Cool. So this dive is really for you, our listener, as we explore these powerful ideas together.
And what's really fascinating, I think, is how a problem that sounds so abstract, dividing a sequence of numbers, actually underpins so much of our digital world.
Right.
Yeah, we're talking about situations where systems are constantly needing to slice and dice these continuous streams. It could be data, workloads, even how memory is organized right inside your computer. And you're right, it's often invisible to us, but it's absolutely critical for performance, stability, even the security of the systems we rely on every single day.
It really is everywhere, isn't it? It's like, picture a continuous flow of information, almost like a conveyor belt, but each item on that belt has a totally different size or importance.
Yeah, different weights.
Exactly, weights. And the crucial things here are 2 things, really. First, these elements arrive in a fixed order. You can't just shuffle them around to make it easier.
Nope, the sequence matters.
And second, they carry highly irregular weights. One item might be tiny, almost nothing, right? The next one could be enormous, a huge chunk of processing. Then another small one. It's all over the place.
Precisely.
Yep.
And the consequences of not handling this slicing and dicing properly, they can be pretty catastrophic. Let's look at some real-world examples from the source material. They really drive this home.
Okay, yeah, let's do that.
So consider load balancing shards in distributed databases. Think about, the huge online services, Google, Amazon, any big social media platform.
Massive scale.
Massive. They store just tons of data across thousands of servers, right? And this data is partitioned into what they call shards. Each shard handles a piece of the data, and the user requests for that data.
Got it.
Now, if you partition this unevenly, let's say you just make simple sequential cuts in a stream of user activity or maybe new data coming in, you can easily end up with what they call hot shards.
Hot shards. Okay.
Like overloaded.
Exactly. It means one single server ends up holding all the data for maybe your most active users or the most frequently accessed info, like a trending news story or a super popular product.
So one server gets hammered.
Totally hammered. That single shard becomes a massive bottleneck, gets overloaded with requests, slows way down, and can even lead to system-wide slowdowns or, total outages for millions of users.
Wow. Okay.
So the goal, obviously, is to distribute the workload, the weight of the data, and requests as equally as possible across all those shards. That keeps things running smoothly and stops failures.
Makes sense. So that's one big area. What else?
Then there's the equally vital challenge of fair cache ways in UMA memory controllers. This sounds technical, but it affects your everyday computer.
Okay, bring it down. In modern multi-core processors, the way different parts of your computer's memory get accessed isn't uniform. Some memory banks are local to a processor core, super fast. Others are remote, and they're slower to get to.
Right. NUMA, non-uniform memory access.
Exactly. So cache partitioning algorithms have to decide how to allocate these contiguous chunks of really fast cache memory, called cacheways, to the different processor cores. Now, if one core, maybe it's running a critical app, gets an unfair, disproportionately large share of the memory pages that are used a lot, it can basically starve other cores that also need quick memory access. This creates bottlenecks, degrades your whole system performance, makes your computer feel sluggish, maybe apps freeze.
Ugh, hate that.
Right, so a balanced memory layout across these cacheways is absolutely paramount for efficient multi-core processing.
Okay, so databases, memory, what about media?
Good one. We also see this principle in contiguous media segments in adaptive streaming, like when you're watching Netflix or YouTube.
Yeah, all the time.
Your device isn't downloading the whole movie at once, right? It's constantly grabbing video segments or chunks.
The little pieces.
Little pieces.
Yeah.
And these segments, they don't all have the same size or byte rate. They vary based on video quality, how complex the scene is, how it's encoded, which directly translates to different file sizes. Those are their weights.
Ah, okay. So some chunks are heavier than others.
Exactly.
Yeah.
The streaming platform needs to manage how these chunks are delivered and buffered to make sure playback it adapts to your network conditions. But if the partitioning isn't done smartly, like maybe it sends too many large high bitrate chunks when your connection is weak.
Buffering.
You get those frustrating buffering stalls.
Yeah.
Or, a sudden jarring drop in video quality. It's all about balancing those weighted segments for a seamless experience.
Fascinating. It's everywhere. Any more examples?
Yeah, one more, which is maybe less obvious, but really interesting. Timeline splits for privacy errors in differential logging.
Differential logging for privacy.
Imagine a company collects tons of user activity data, maybe for analytics or improving services. To protect user privacy, they might batch user events into eras, like time periods, and apply a strict privacy budget to each era.
Okay, like a spending limit for privacy?
Kind of. But here's the catch. User events aren't uniform in how much information they carry. Some events have a lot of sensitive or unique data. Those are heavyweights. Others contain very little lightweights.
Right.
So how do you draw the boundaries between these eras to make sure the privacy loss is spread out evenly over time? You want to avoid situations where one era accidentally leaks way more information than another, or uses up the whole privacy budget too fast.
Whoa, that's a tricky balance.
It's a really delicate balancing act to ensure fair privacy guarantees over time.
So, okay, in all these incredibly different cases, databases, memory, video, privacy logging, we have a sequence of items. They could be data records, memory pages, video chunks, user events, whatever. Each has a different weight, and we need to cut them into a fixed number of bins or groups. The common thread, it seems, is always about minimizing the imbalance across these K-target bins.
Exactly. Minimize the imbalance.
All while respecting some fundamental rules about how we make those cuts. It's a universal problem, really.
Precisely. And in our sources, this gets formalized. It's called optimal sequence partition under quadratic fairness loss, or OSPQF for short.
OSPQF, okay. That's quite a mouthful, yeah. But it definitely describes a problem that's, everywhere. So how complicated can cutting things really be?
$1 million question.
We're about to find out, I guess. We're going to see that this problem, in its most general form, is what computer scientists call NP-hard. Which is basically CS speak for solving this perfectly and quickly is probably impossible.
Right. The no free lunch theorem of computation.
Pretty much. But then we'll explore some classic and some really novel solutions that manage to find excellent compromises. And we'll even touch upon some cutting-edge convex optimization techniques. These try to bridge that gap between, impossible and provably good.
Sounds like quite a journey.
Okay, let's unpack this then. Maybe let's start with an example. Something that will hopefully shatter your intuitions about fair division, show you just how tricky this can get.
Okay, hit me with it.
All right. Imagine we have a sequence, 112, 2 elements, could be data packets, video chunks, whatever. Their weights reflecting their size or importance are 7, 3, 19, 1, 11, 5, 2, 17, 13, 2, 1, 23.
Got it. A dozen numbers.
Our goal, partition these into Quest Ray 3 bins, and we want approximately equal total weight in each bin.
Okay, 3 bins, roughly equal weight. First step, we need to know what that approximately equal target actually is, right?
Yeah, what's the ideal?
So If we sum all those weights, 7 plus 3 plus 19, all the way to 23, we get a total weight of 104.
Okay, what a whole total.
With KT33 bins, our ideal, perfectly balanced sum for each bin would be the total weight divided by dollars. So 1 mu to fun N43, which is about 34.67.
34.67, that's our target mean.
Exactly. That's the bullseye we're aiming for in each bin. Now let's try the most intuitive approach. A naive contiguous split. Just means we cut the sequence at 2 points.
Okay, where do we cut?
Let's say we make our cuts after index 4 and index 8. What do we get?
All right, so bin 1 gets items 1 to 4.
Which are weights 7, 3, 19, 1. Their sum, $71, is 30.
30, okay. Bin 2 gets items 5 to 8.
Weights 11, 5, 2, 17. Their sum, 7 threes, is $35.
35. And bin 3 gets the rest, 9 to 12.
Weights 13, 2, 1, 23. Their sum, $33 is $39.
Okay, so sums are 30, 35, and 39. Our target was 34.67. They're all kind of close.
That seems not terrible, right?
Yeah.
Reasonably close. But how do we quantify how fair this actually is? We calculate what's called the fairness energy. Filer.
OSPQF thing, quadratic fairness.
Right. We use the formula $1 sum SJ mu 2. So we square the difference between each bin's sum and that ideal mean, 34.67, and then add up those squared differences.
Squaring makes bigger errors count more.
Exactly. It heavily penalizes large deviations. So for these sums, 30, 35, 39, our sources tell us this contiguous split gives $4 a prots, $58.999. That's our measure of unfairness for this intuitive cut.
58.9. Okay. Seems like a number. Is it good? Bad?
Well, let's compare it.
Here's where it gets really interesting. Potentially mind-bending. What if we could break the rules? What if we didn't have to make contiguous cuts?
What if we could pick and choose?
Exactly. What if we could pick elements from anywhere in the sequence as long as we put every element into exactly one bin? This idea of a spectral pairing algorithm suggests just that. It's non-contiguous. It works by finding hidden patterns, almost like a secret rhythm in the data.
Okay, intriguing.
So after running an algorithm like this, maybe cleverly searching for the best non-contiguous arrangement, it could potentially produce bins with sums of 34, 35, and 35.
Whoa, 34, 35, 35. Those were much closer to the target of 34.67.
Right. Let's quickly recalculate the fairness energy for this surprising result.
Okay, so $5, $34, 67.7, 2 plus...
$633.
So $5 is about 0.67.
0.67. Okay, now for the big reveal. We went from a fairness energy of $5 approx, $58.09 with the best contiguous split.
Well, that seemed pretty reasonable.
To an astonishing $5 approx 0.67 summon with the spectral pairing algorithm.
That's a huge difference, like what, 80 or 90 times better?
The source says roughly 30 times reduction in fairness loss, but yeah, it's an incredible improvement. The surprise is profound.
Yeah.
Pairing far apart indices, doing it in a structured, rhythmic way, can absolutely crush every contiguous scheme you could ever devise.
Wow.
It's like the data has this secret hidden rhythm and only certain types of non-obvious cuts can actually reveal and exploit it.
Okay, that does shatter intuition.
Yeah.
So how does that magic happen? We need to get more precise, right? Define this OSPQF problem more rigorously.
Yeah, let's nail down the details.
All right. First, the input parameters, n. That's the length of our sequence. In our example, n was 12. K. The number of partitions or bins we want must be 2 or more. In our example, K was 3, W1 doc and N. This is the array of positive, real-valued weights for each element. Each Y is positive, representing its size or importance.
Simple enough. Sequence length, number of bins, and the weights themselves.
Right. Now the crucial part, 3 partition models. The rules for how you're allowed to make cuts fundamentally change the problem's nature and difficulty.
Okay, what are the models?
1. Contiguous. This is the model from our first attempt. You define K1 cut points. Elements stay exactly in their original sequence order within each bin. Bin 1 gets elements 1 to cut 1, bin 2 gets cut 1 plus 1 to cut 2, and so on.
Simple, linear, the intuitive way.
Exactly. But it can miss those hidden structures. 2. Modular index. This is the trick behind our surprising example. It's non-contiguous. Elements don't have to be neighbors in the sequence to end up in the same bin.
How does it decide where things go?
It uses a mathematical rule. Element I gets assigned to bin J, using J equals she pi plus mod K.
Whoa, okay. Pi phi mod K. Break that down.
Think of P as a stride, or frequency. It controls how far apart indices are selected to be in the same bin. If P1 is like dealing cards round robin. If P is bigger, you jump further. There's a phase or offset. It just shifts the starting point of the pattern.
So it sort of interleaves elements across bins based on this P and phi.
Exactly, in a structured, rhythmic way.
Yeah.
It lets us pick elements far apart that might balance each other out. 3, general pairing. This is the most flexible model. Total freedom. You can assign any index I to any of the K buckets arbitrarily. Yeah. No rules based on index position or modular math. Just put them where you want them.
Maximum flexibility. Sounds powerful, but maybe hard to figure out.
Precisely. That freedom comes with a significant computational cost, as we'll get into.
Okay, so 3 ways to cut. Contiguous, modular index, the rhythmic way, and general free-for-all. But no matter which rules we play by, the goal is the same, right? Minimize that objective function, the quadratic fairness loss.
Exactly. Let sub each $J be the sum of weights in bucket J. We already defined one U as our target mean, total weight K. The formula for fairness loss, $5 as always. And remind us why the quadratic part, the squaring, is important.
2 main reasons. First, mathematically, it's gradient friendly. That means optimization algorithms can often find the minimum value more easily. It's a smooth function. Second, and maybe more intuitively, it heavily penalizes large deviations from the mean Joel.
Right, one big outlier hurts way more than a few small ones.
Exactly. If one bin's sum is way off, that squared difference adds a lot more to the total loss, $5. Think of it like physics. Imagine springs connecting each bin's sum sub each $J target mean fits a scalar. This quadratic loss is like the total potential energy stored in those springs. We're trying to find the configuration with the lowest energy, the most relaxed, balanced state.
Cool analogy, like finding the least stressed arrangement.
Precisely. And while other ways to measure fairness exist, like using absolute differences, this squared L2 norm is very common and has nice properties. Wow, okay, so it's not just about getting close, but really punishing those big errors. That makes intuitive sense for system stability, doesn't it? If one server is massively overloaded, that's worse than a few being slightly busy. So, putting it all together, we're trying to find the best way to group these weighted items using one of these rule sets, contiguous, modular, general, to make the sums in each group as close as possible to the ideal average, non-exality, and the cost of unfairness measured by this quadratic loss skyrockets if any group is way off that average, makes those big imbalances really painful.
You got it. And this naturally leads to the next big question. How hard is it to actually find that perfect partition? Which brings us to the hard truths of computation. Complexity theory time.
Uh-oh. That sounds serious.
Let's start with the most flexible model, general assignment. If we ask the decision version, can we find any partition with a fairness loss less than or equal to some value to tool? This is actually a special case of the famous balanced partition problem, which is known to be NP-complete. Basically incredibly hard to solve exactly for large inputs. Think finding the perfect needle in an exponentially growing haystack.
So no fast, guaranteed optimal solution for the general case.
Worse than that, actually. For our specific quadratic loss, it's strongly NP hard. This is a stronger kind of hardness. It means that even if the weights themselves were nice, small integers, there's still no efficient algorithm that guarantees the absolute best solution in polynomial time. Not unless PNP, which most people think is unlikely.
Okay, takeaway. Exact optimality for general assignments. Forget about it at scale.
Pretty much. If you have millions of data points and can put them anywhere, finding the absolute perfect partition is computationally hopeless in any reasonable time frame. It'd take astronomical amounts of time.
Okay. But what about the simpler case, the first one we tried?
Contiguous partitioning with K fixed. Now this model is much more tractable. Because it has properties like optimal substructure, meaning optimal solutions are built from optimal subsolutions and overlapping subproblems, meaning we solve the same smaller problems over and over.
Sounds like dynamic programming.
Bingo. This structure makes it perfect for dynamic programming, or DP. A classic DP algorithm for this runs in AN2 time.
Okay, KN22. Better than exponential, but still. Quadratic in N. Could be slow if N is big.
It can be, yes. But it's polynomial time, a huge improvement over NP hard. And as our sources mention, this can often be optimized further down to AN using some clever tricks, like pre-calculating prefix sums to find segment sums instantly, and sometimes more advanced techniques exploiting the quadratic cost functions properties.
That's much better. That might actually be practical for a larger N.
It often is. But the key is we had to add that strong contiguous constraint to make it efficiently solvable.
So it's fascinating. Just changing the rules slightly takes the problem from practically impossible to computationally difficult but feasible. Yeah. If you tell a computer, make it fair any way you want, it basically gives up on finding the perfect answer quickly. If you say, make it fair, but you can only make straight cuts, suddenly it becomes a problem we can tackle, even if it takes some computational effort.
Exactly. The structure you impose matters enormously.
Okay, so given these complexity realities, how do people actually approach OSPQF in the real world? We need practical solutions, right? Baselines to compare against. What are the classic approaches people would try first?
Right. Well, for the contiguous case where we are restricted to sequential cuts, the main baseline, the gold standard for optimality, is that dynamic programming approach we just mentioned.
Even though it can be slow.
Even though the only two version is slow.
Yeah.
Because it guarantees the best possible contiguous partition. It uses that principle of building up solutions from smaller ones.
How does that work again, intuitively?
Imagine you want to find the best way to cut the first n items into k-bins. Let's call that cost dpkn. To figure that out, you basically try out every possible place for the last cut point, say m.
Okay.
You look at the cost of the best partition for the first m items into k1 bins, which you've hopefully already calculated, and you add the cost, the square deviation, of just that last segment from m plus 1 to n. You try all possible m's before n and pick the one that gives the minimum total cost for dpkn.
I see. Building it up piece by piece, trying all options for the last piece.
Exactly. And to make this reasonably efficient, you absolutely need prefix sums. Remember, prefix is just the sum of weights W1 up to Wx.
Right. Pre-calculate those sums.
Yeah. Then you can find the sum of any segment, say Wm plus 1 to n, in constant time omega dollars, just by calculating pre-mm. Without that, calculating sums over and over would make it totally kn $3, which is way too slow.
Got it. Prefix sums are key.
So even with prefix sums, the time is discard and space is s of. If n is, say, 10,000 and k is 16, that's roughly 16 times 100 million, 1.6 billion operations. That's still very, very slow, as the source says, impractical for really huge n. But it is the optimal answer for the contiguous case. It's the benchmark.
Okay, the slow but perfect contiguous solver. What's the alternative if you need speed?
At the complete other end of the spectrum, for sheer speed, you have the greedy two-pass algorithm. This is a heuristic, a rule of thumb, not guaranteed optimal, but fast.
Greedy. Sounds simple. How does it work?
The first pass is dead simple. You just walk through the sequence, adding elements to your current bin. As soon as the current bin sum hits or goes over the target, boy, bam, you make a cut. Start a new bin, repeat till you're done.
Filling buckets one by one till they're roughly full, then moving on.
Exactly. Very straightforward. Then there's usually a second pass for local refinement. It goes back through the cuts it just made and checks if small adjustments improve things. Like maybe moving the last element from bin J over to bin J plus 1, or vice versa. Does that reduce the overall fairness energy F?
Little tweaks.
Yeah, it does these local swaps iteratively until it can't find any more easy improvements, or maybe just for a fixed number of tries.
And how fast is this?
Empirically, it's often incredibly fast, like dollar time, lightning fast.
Wow. Okay, so what's the catch?
The catch is accuracy, or lack thereof sometimes. The source warns it can be catastrophically wrong on certain sequences, especially ones designed to trick it, adversarial weights.
How so?
Because those initial greedy choices in the first pass might lead it down a really bad path. It can get stuck in what's called a local optimum, a state where small changes don't help, but the overall solution is actually terrible. It can't see the bigger picture to undo its early mistakes.
Like taking a wrong turn early and ending up way off course.
Precisely. Our sources say it can lead to solutions with fairness loss, 5-10x worse F than the optimal DP solution. It prioritizes speed, but you might pay a big price in fairness.
So, okay, we have the slow but perfect DP for contiguous cuts, and the super fast but sometimes horribly inaccurate greedy approach. This really highlights why we need something else, doesn't it?
Exactly. There's a big gap there.
Which brings us back to that surprising aha moment we had earlier. Remember that example? Where the non-contiguous split totally crushed the optimal contiguous one, cutting the fairness loss by like 30 times.
Yeah, the 58.9 versus BNU 0.67. Still amazing.
How did it do that? This is where our spectral pairing algorithm comes back in. And what's so fascinating, it just looks at the problem completely differently. It sees the data with new eyes almost.
Right, the intuition shifts. Instead of thinking of the indices 1 to n as just a straight line, spectral pairing invites us to imagine them as forming a cyclic group, math BBZ to n.
Like arranging them on a circle, where after n comes 1 again.
Exactly, wrap around. Now, instead of making linear cuts, we pick elements based on a repeating modular pattern around this circle.
That's the modular indexing thing again. J plus mod K.
Correct. Let's re-unpack P, and Phi is the stride, or frequency. It determines how far apart in the original sequence elements are when they get grouped together. P1 is simple round robin. A larger P means wider jumps, grabbing elements that are much further apart linearly. As the phase shift or offset, it just slides the whole pattern along, deciding where the assignment sequence starts, which bin gets element 1, without changing the repeating pattern itself.
Okay, so P controls the rhythm, controls the starting beat.
Nice analogy.
Yeah.
And the core hypothesis here is, if the weights themselves have some kind of hidden rhythm, some periodic structure, or maybe a subtle arithmetic pattern.
Which we talked about earlier, like daily patterns in work.
Right. Or harmonic frequencies in sensor data, or even those weird regularities in prime numbers. If that structure exists, then there might be a magic pair of P. This specific combination of stride, P, and phase will systematically interleave the heavy and light elements across the K-bins in just the right way. It aligns them so that their sums end up incredibly close to the target Minoji. It's like finding the perfect riffle shuffle for a deck of cards that wasn't random, but had a subtle order you could exploit.
That's a brilliant idea, exploiting hidden order. But we mentioned real-world examples, workload traces with daily, weekly patterns, sensor data harmonics, memory access strides.
Exactly. And the source even mentions the inspiration from number theory. Weights like $1 or 3-1 is the Iloff prime. Even the primes have these subtle arithmetic regularities that modular indexing can pick up on. It's not always obvious repeating patterns. It can be deeper, nonlinear correlations.
So how does the algorithm find this magic P pair? Does it need complex math?
Surprisingly, no. That's the beauty. Instead of trying to solve the general non-contiguous problem, which is NP hard, it just does a focused brute force search over a small space of likely P and Fab values.
Brute force. Doesn't that sound slow?
Only over a small space. For P, you might only search from 1 up to some reasonable maximum, P max, say 100, or maybe a few hundred. You don't usually need astronomically large strides. For phi, you only need to check values from 0 to K1, because the pattern repeats every K steps.
Ah, okay, so it's not searching everything, just likely candidates for P and phi.
Right. For each P, in that limited search space, you quickly calculate the resulting bin assignments using the mod K formula, sum up the weights in each bin, calculate the fairness loss phi, and then you just keep track of the P pair that gave you the minimum failure you saw.
Simple but clever. What's the complexity then?
The complexity is roughly AP max, AIMBAX times N.
P max times non-dollar. How does that compare?
Well, since P max, like 100 and K, like 16, are typically treated as small constants in practice, this algorithm is effectively linear in NaN.
Whoa, linear. That's a huge improvement over the Tanimax or even Nolligans of the contiguous DP.
Massive improvement in speed.
Yeah.
And empirically, on data that has this kind of structure, like synthetic log spaced or harmonic weights, this spectral pairing approach beats DP by orders of magnitude in terms of the fairness loss $5 sheaved.
So it's faster and potentially gives a much, much fairer result.
On the right kind of data, yes. It's not a general optimal solver for any data distribution. But if your data has that hidden rhythm, spectral pairing is like a turbocharged approximate solution that delivers stunning results. It's incredibly powerful where it applies.
So, wow. By changing the rules of cutting, by introducing this totally different kind of structure, this modular rhythmic assignment, we can find unbelievably better solutions. It's not about being perfectly optimal in the general impossible sense, but about being brilliantly approximate by exploiting the specific nature of the problem. It's like finding a secret key that unlocks this hidden efficiency, giving a truly profound boost in fairness.
Well put. It leverages structure that other methods ignore.
Okay, so that's DP, greedy, and spectral pairing. But you mentioned something even more, cutting edge. For those who want to push the boundaries, maybe get guarantees even for the general assignment case. Something about continuous optimization.
Ah, yes. For the adventurous, we delve into Convex, Relaxation, and mirror Prox. This is where things get mathematically quite sophisticated, but the core idea is elegant.
Lay it on us.
So remember the fundamental challenge with general assignment. Our decision variables, Cij is item I and bin j. They have to be 0 or 1, discrete, binary.
Right. That discreteness is what makes it NP hard.
Exactly. So the core idea of relaxation is to, well, relax that constraint. We soften it. Instead of Cij being only 0 or 1, we allow it to be any real value between 0 and 1 inclusive.
So like a fraction. Item I could be 70% in bin 1 and 30% in bin 2.
Precisely. Cij now represents the fraction of item I assigned to bin j. We still keep the rule that each item has to be fully accounted for. So for any item I, the sum of its fractions across all bins j must still equal 1. Cij mine.
Okay, but how does allowing fractions help? We still need a Zoran answer in the end.
Ah, but here's the magic. When you allow these fractional assignments, the quadratic fairness loss function of IOT by becomes a convex function, and the set of all possible valid fractional assignments, that forms a convex set.
Convex, meaning like bowl-shaped. No weird bumps or valleys to get stuck in.
Loosely speaking, yes. Convex optimization problems have this wonderful property that any local minimum is also the global minimum, and there are efficient algorithms guaranteed to find that minimum. Unlike the treacherous landscape of discrete optimization, convex optimization is, relatively speaking, paradise.
So by pretending items can be split, the math becomes much easier.
Much, much easier and more powerful. We can even frame the problem elegantly as a saddle point game. Imagine two players.
Okay.
The primal player controls the fractional assignment CIOT and tries to minimize the fairness loss, randomness TD. The dual player controls some abstract prices or Lagrange multipliers, lambda, and tries to maximize a related objective, effectively pushing the bin sums to head towards the target formula.
A min-max game, like game theory.
Exactly. The goal is to find a saddle point, which is like a Nash equilibrium. It's a state where neither player can improve their outcome by changing their strategy alone, assuming the other player stays put. This saddle point corresponds to the optimal fractional solution.
Okay, cool concept. How do you find that saddle point?
That's where algorithms like mirror Prox come in. The source calls them a beautiful, powerful class of algorithms.
Mirror Prox, what's the intuition?
It's an iterative algorithm. It takes steps towards the solution, but it's clever. It doesn't just take one step based on the current gradient. It performs a kind of predictor-corrector sequence. It takes an initial step, the prediction, sees where that leads, and then uses that look-ahead information to compute a better, more stable second step, the correction.
Like looking before you leap, then adjusting your leap.
Sort of, yeah. It helps ensure stability and allows for faster, more reliable convergence, especially in complex settings. It often uses something called a mirror map, maybe based on entropy, to handle the constraints, like keeping Cij day between 0 and 1 and summing to 1, more naturally than standard Euclidean steps. It converges nicely, often with guarantees like OT convergence rate after T iterations.
Okay, so mirror Prox finds the best fractional solution, but we still need a real-world answer where items are either in a bin or not.
Absolutely. The direct output is fractional, so the necessary final step is rounding. You need a strategy to convert those fractions Cij back into hard zeros and ones. This isn't trivial. You want to do it in a way that introduces the least possible extra unfairness compared to the optimal fractional solution.
Yep.
Techniques like randomized rounding, assigning item I to pin j with probability Aij, or clever swap-based rounding exist for this. It's a crucial bridge back to the discrete world.
Got it. So relax to fractions, solve the easy convex problem using something cool like mirror Prox, then round back to a discrete answer.
That's the essence. And the significance is huge. It's considered the most modern and principled way to tackle these really hard general partitioning problems. It offers algorithmic guarantees on convergence and solution quality, and it connects directly to the cutting edge of large-scale optimization theory. It gives us a way to approach the truly hard version with confidence.
Wow. Okay, from simple straight cuts to searching for hidden rhythms with modular math, and now to this sophisticated game theory, convex optimization approach, finding the fairest fractional split, then rounding. It really shows the incredible depth hidden in this seemingly simple problem of just cutting things up fairly.
It's a testament to how deep CS theory can go to solve practical problems.
So if we zoom out again, connect this back to the bigger picture. You said earlier this isn't just a niche problem.
Absolutely not. What we've been dissecting here, if you strip away the specific applications like databases or video, is truly a canonical computer science problem.
What would you call it, generically?
Maybe something like minimum imbalance partitioning over weighted sequences. It's a fundamental challenge that pops up everywhere.
And you mentioned it's related to other classic problems.
Definitely. It's a fascinating hybrid, pulling ideas from several places. One, balanced partitioning problem. The classic NP hard task of dividing elements into k-sets with sums as close as possible. Our problem adds a crucial sequence constraint and sometimes specific structure. Two, min sum of squares clustering. It's like a 1D version of k-means, but instead of minimizing variance around a cluster center, we're minimizing the total square deviation of bin sums from a uniform target already made up. It's about equal mass, not proximity. 3, subset sum bin packing with a fairness twist. You're trying to fill bins to a uniform weight, but items are indivisible in the discrete cases. Our problem explores how this behaves with fairness metrics and structured inputs. 4, fair load balancing over time or space. At its heart, it is load balancing. The cuts are assignment boundaries. The fairness energy measures load imbalance. We want optimal resource use.
So what looks like a specialized issue for, say, Google's database sharding or Netflix's streaming is actually a deep fundamental computer science challenge. It pulls together ideas from complexity, algorithms, optimization, even number theory. That really feels like a true deep dive.
Exactly. But what makes this specific version we focused on, the OSPQF, with these different models, really special?
Yeah, what distinguishes it from those other classics?
A few key things based on our source. First, the potential spectral structure of the weights. The idea that weights might not be random, but have nonlinear arithmetic correlated spacing, like those primes or periodic patterns. Exploiting that structure is key. Second, the introduction of a global pairing rule, specifically those modular cuts, PI+. This creates non-contiguous but symmetric segmenting. That's quite different from typical partitioning, which often focuses on locality. This is non-local balance finding. And third, minimizing this specific physical style action functionalism, the quadratic loss, $5. It's more than just a metric. It has that spectral interpretation, behaves like potential energy. It's a robust way to quantify imbalance that works well with these algorithms.
So TLDR.
TLDR. It's about optimal segmentation of weighted sequences under a fairness loss function. And methods like spectral pairing are domain-optimized heuristics for global weight smoothing. They're tuned for data with hidden arithmetic patterns, which puts them way ahead of traditional partition algorithms for those specific cases, because they basically speak the data's secret language.
That's a fantastic summary. A deep problem with surprisingly clever solutions tailored to hidden structures. It really reminds us that even basic tasks like cutting can hide incredible complexity and lead to brilliant algorithms. Okay, as we start to wrap up this deep dive, let's try and distill the most important nuggets of knowledge for you, our listener.
Let's crystallize it.
First, I think, is the profound insight that looks random does not necessarily mean no structure. Data might seem chaotic, weights might seem arbitrary, but hidden rhythms, arithmetic correlations, they can absolutely exist.
Don't judge a sequence by its cover.
Right. And smart algorithms, like that spectral pairing, are designed to find and exploit these subtle patterns. They can just annihilate imbalances that simpler, local, contiguous cuts completely miss. So maybe the next time you look at a stream of numbers, ask yourself, is there a hidden pattern here waiting to be found?
Good takeaway. What else?
Second, the choice of partition model is everything. How you define the rules of cutting strictly contiguous, flexibly modular, or totally general fundamentally changes the game. It impacts the difficulty of finding a solution and the quality of the best possible outcome you can even hope for.
The constraints shape the solution space.
Exactly. A restrictive model might make it solvable, but you might miss out on far better solutions. Understanding the constraints you're working under, or maybe could work under, is step one.
Makes sense. And third,
we've seen this powerful trinity of approaches, right? There's the slow but exact dynamic programming for contiguous cuts, the guaranteed optimum under strict rules. There's the fast but potentially flawed, greedy heuristic, quick and dirty, great for speed, but sometimes spectacularly wrong. And then there's the turbo-approximate spectral pairing, which can be incredibly effective on rhythmic data, giving amazing gains.
the three main tools.
Plus, we touched on the really advanced world of convex relaxations, using things like mirror Prox, offering principled, guaranteed approaches for even the most complex general scenarios. It's like having a whole toolkit, from basic hammers to laser scalpels for tackling fairness.
A good way to put it. Each tool has its place.
Definitely.
And maybe one final thought to leave with you, the listener. Given the incredible gains we saw from something as conceptually simple yet profound as modular index partitioning just changing the rules of the cut, what other hidden structures might exist? Out there in the data streams we encounter every single day, structures just waiting for some novel algorithmic trick, some new way of looking to unlock a truly fair solution.
That's provocative.
Think about the data you interact with, your own workflow, maybe how information is organized on your screen, how resources get allocated in systems you use. Could a simple arithmetic pattern, a different way of seeing the sequence, dramatically improve how things are balanced, how information gets presented? It's a compelling thought, maybe for your next deep dive into the world around you.
Yeah.
Because fairness, ultimately, isn't just some abstract ideal. It's something actively engineered, or sometimes, unfortunately, misengineered into our digital lives.
That's a perfect place to end. Thank you for joining us on this deep dive into algorithmic fairness and optimal sequence partitioning. It's a problem, as we've seen, that impacts everything from internet speed to data privacy, all hinging on how we decide to slice up weighted sequences.
It's been fascinating.
We really hope you'll reflect on these concepts and maybe start looking for those hidden rhythms yourself in your data or in the systems you rely on. Until next time, keep digging deeper.
So this was episode 37 of SpaceTime Cafe. Thanks for watching.